Hi, and welcome to the videos for lecture 16 of privacy in machine learning and statistics. So today we're going to start by recapping and somewhat reformulating the guarantee we got from the multiplicative weights algorithm we covered last time. We'll sort of formulate its guarantee in terms of how well it does as an algorithm that decides on distributions over actions, like as a vector rather than single actions. Then we'll talk about how we can, one of the ways we'll turn to the query release problem, doing that with differential privacy, and we'll talk about how we can do query release using algorithms that produce what we'll call synthetic data distribution. So this is like a distribution over the data universe that behaves kind of like the data set, at least with respect to the queries we care about. And finally, the bulk of the lecture is going to be about this connection between online learning and query release via synthetic data. And specifically, we'll see this one algorithm called multiplicative weights via the exponential mechanism, or MWEM for short. And we'll see exactly what it, what it gets us. So, before we go into the actual material, let's just try and get a preview of what we'll get out of this. All right, so what will we get? Okay, so we're going to get a new algorithm for query release. So if you recall, we've got in the query release problem, we have a set of k linear queries. Turns out they don't actually have to be linear, but that's what works best. And last time we had a parameter m. When we talked about the projection mechanism, we had a parameter m, which was the size of the universe of possible records. Okay. And so when we used like the Gaussian and Laplace mechanism for query release, when we just added noise to each of the queries, what we got was L infinity errors. So this meant that like each of our answers was accurate to within some parameter alpha. When n was at least some quantity, and how big did n have to be to get accuracy alpha? Well, we'll call this n sub Gaussian. So we had some constant that depended on epsilon and delta, which was about square root of log 1 over delta over epsilon times square root of k log k all over alpha. Okay. So if we just sort of reformulate the guarantee for the Gaussian mechanism in terms of how much data do we need to get a certain level of accuracy, this is what it looked like. On the other hand, if we looked at the projection mechanism that we saw last time, 2 lectures ago, then it had a different kind of error guarantee. So it had an L2 error guarantee. And we normalized it so it still made sense to compare it, so that it was still like, between 0 and 1. And that quantity was alpha when the sample size was at least some other number, and I'll call it n projection, which was sort of some constant depending on epsilon delta, not exactly the same one, times square root of log m over alpha squared. So this guarantee is different in a couple of ways. First, it's averaged over all the queries, but the cool thing about it is it only depends on the number of possible records in the universe. That sort of, in some sense, that's a reasonable proxy for the dimensionality of the data. Okay, so roughly speaking, when the dimension of the data is d, you get something like square root of d over alpha squared. Okay, no matter how many different queries you're asking. Now, the hitch here is that you don't get all of them accurately. Well, all you know is that your accuracy is good on average. Okay, today we'll see this MWEM algorithm, and it will give us an L infinity error guarantee. All right, and this will have yet another form. So it'll have some other constant depending on epsilon and delta, basically again, square root of log 1 over delta all over epsilon. And this will have a guarantee of involving both of these parameters. So it'll be log k square root of log m, okay, over alpha squared. So relative to, say, the Gaussian mechanism, it has the same type of error guarantee, L infinity, but it has a worse dependency on alpha. And it's picked up this dependency, albeit a reasonably mild one, on the dimensionality of the data. But the big benefit is that it now has only a logarithmic dependency on the number of queries that we care to answer. So, for example, let's look at some specific classes. So for thresholds, let's just compare what we get with the Gaussian mechanism and this new multiplicative weights mechanism that we'll see today. So for thresholds, k is equal to m is the same. They're the same, okay? And so, I'll just call it, m. And so we'll get something like the MWEM guarantee will tell us that we need sample size at least, and I'm dropping the constants here. So maybe I'll put an approximate just to be clear. So something like n log to the 3/2 m over alpha squared. Whereas, the Gaussian mechanism that we saw before had something like that sort of similar dependency on the logs, but over alpha. Okay, so actually for the thresholds family, the binary tree, this was sort of with the binary tree improvement that we saw in lecture 5. So if we combine the binary tree idea with Gaussian noise, we get some guarantee that's roughly along these lines. And so the dependency on the range of the data will be similar. The exponent actually depends exactly what you're measuring, but the dependency on alpha, on the target accuracy, is now much better. Okay, so sort of for these queries, hasn't really bought us much. But we can look at even slightly more complicated families of queries, and we'll see a big difference. So one interesting family of queries are what are called pairwise marginals. So here, my data universe, for simplicity, we'll think of it as binary strings of some length little d. And the thing we're interested in is for every, so each record is a vector of d attributes. And the thing we're interested in is how many, for each pair of attributes, what are the pairwise statistics? Like with what frequency do both of those attributes appear as 1, both as 0, the first one is 1 and the second one is 0, and vice versa. So I won't write down all of those queries, but like a subset of those queries that's interesting is when the little phi function that defines the query that I'll remind you of this notation in a little bit, but we'll just go through quickly here. So this is 1 if on input x, if xi equals to, so it's specified by 2 attributes, two coordinates of the vector. If both of those coordinates are equal to 1, then we count that, and 0 otherwise. So the corresponding query counts in how many positions in how many records of the data set are both of these attributes set to 1 at the same time. Okay, so here the size of the universe is 2 to the d, and the number of queries is something like d squared. And already for these queries, we see an improvement. So the MWEM sample, the sample size we need to get, a guarantee, an alpha L infinity guarantee with MWEM is now going to be something like, so the square root of log M term, that's actually going to be the big one, right? So it's going to be square root of D times log K, and that's only about log of D. So that actually won't be a big deal over alpha squared. Okay, versus what we would get for the Gaussian mechanism, which would be something like D square root of log D over alpha. Okay. So again, what we see is like the MWEM mechanism is going to allow us to add like much less noise. And in particular, this is sort of going to give us like an interesting way to exploit like dependencies in these pairwise marginals that the Gaussian mechanism and indeed the factorization mechanism can't really take advantage of. All right. So take a quick break and then we'll dive right into it.